Excellent. So our last talk of the day is by Roy Levin, and he's a Fulbright fellow in Tel Aviv University, and he'll be talking about online covering problems in a variety of models. So over to you.
Thanks. Okay, thank you for the organizers. Thank you all for staying until now. Hopefully this will be interactive. So please, I have maybe an hour's worth of content that I can share, but I'd rather we do like half of that well. And so, yeah, best is interactive, ask me questions as I go. Okay, so my name is Roy. Today I'll be talking about online covering, secretaries, profits, and universal maps. This is joint work with Anupam and Greg Keeney at Harvard. And this is based on a paper at Fox last year and some forthcoming work. So it's kind of a blend. Okay, we'll be talking about set cover. What's set cover? I have M sets and N elements, script S and script U. Okay, I'm thinking of the set system as a bipartite graph. Okay, the sets are on the left, the elements are on the right, and there's an edge between a set and an element if the set contains the element. What's the goal? Pick the smallest number of sets to cover all the elements. Okay, smallest number of left-hand side vertices such that every right-hand side vertex has at least one set adjacent to it. Okay, what do we know about this problem? Classic NP-complete problem. You can get if you can't get the optimal solution in polynomial time, but you can get log n plus 1 approximation. Okay, the simple greedy algorithm gets this, and this is a classic result. Okay, we'll be talking about a variant of this problem, which was introduced by this by now kind of classic paper of Alon, Arabuch, Azal, Buchbinder, and Noor. Azal and Noor are here in the audience with us, Sefi and Yossi. And it's the following. Okay, it's the same set cover problem, but we don't know the elements ahead of time. Okay, they're going to show up over time. At the beginning, we know nothing basically. Okay, we just have this this left-hand side. Every time an element shows up, it's our task to pick a set to cover it if it's not already covered. Okay, so for example, this first element shows up and we'll pick a set to cover it. Another element shows up, it's still uncovered, we need to buy a set to cover it. A third element shows up, it's already covered, no need to do anything, and so on and so forth. And the goal in this game is that the total number of sets that you pick over the course of this process be not too much more than the offline solution to the set cover problem if you had full information and infinite computing power. Okay, so are the rules of the game clear? Great. So what can you do here? It's like clearly, at least as hard as the offline version. Turns out, somewhat amazingly, and this original paper showed this, you can't get quite the log that you can get offline, but you can get log n times log m. So recall m is the number of sets and n is the number of elements. And this is best possible for polytime algorithms, at least. Okay. We'll see actually the intuition, yeah. But it separates very cleanly. It's like a two-stage algorithm. Yeah. Okay. Great. So basically this, this question is fully, this problem is more or less fully understood in the worst case model. And the starting point for our work was the question, what happens beyond the worst case? This is quite a pessimistic model of input. Really, an adversary is like really trying to mess me up with every step. Okay. So there's two natural ways you could relax the adversarial assumption. One is you can relax the order. Okay, so maybe I assume that an adversary fixes an underlying set system, but I don't know it. It's unknown to me. And now this adversary is forced to roll some dice and then reveal the elements in a uniformly random order. Okay, so the adversary rolls dice. It's fixed the set system ahead of time. And now we play the same online set cover game, but in this uniformly random order. This is clear, the model? That's one model. Model two, maybe the order is fixed, so the order is not random anymore, but somehow the underlying instance is random. Okay, and there's maybe a few ways you could do this, but here's one natural way you could do this. Every element is sampled from a known distribution. So I have a sequence, kind of D1 through whatever, Dn, of known distributions that I know ahead of time. And then I play the online set cover game where every time I draw an element from the next distribution. This is clear as well? Wonderful. Okay, what is known about these things? So let's draw a table. And on the x-axis, I have whether or not the instance is random. On the y-axis, I have whether or not the arrival order is random. So we said that in the the bottom right-hand corner, when both are adversarial, that's the online set cover problem. Like the classic fully adversarial one, we said that's log n times log m. All right. In this upper left-hand corner, what can you do? So there's a paper by Anupam and a group of co-authors, very nice stock paper from '08, that shows that if those distributions d1 through dn are the same distribution, okay, you can avoid the double log loss. So you'll lose log m times the support size of that distribution. Is that clear? So I'm drawing n times from some known distribution, and I'm playing online set cover on these draws. Okay. I'm calling this box the secretary model in analogy to the sort of classic packing problem. And this box I'm calling the profit setting. Okay, hopefully these analogies are clear, but this is a covering world, so it's quite a different flavor. And actually nothing was known prior to our work in these two boxes. And we're going to fill them in. So the reason nothing was known was there's some reason to believe that that double log loss is kind of like what you get. Like there's a lower bound. People thought the lower bound held in this setting, and there's a natural barrier. Like the natural algorithm for the bottom right hand corner has this like two stages. Like you asked this question about where the two logs come from. It was sort of natural to assume that was a sort of a barrier even for the random order setting. What we show is, and this is our Fox paper, is that actually there is a polytime algorithm for the secretary version of random order set cover. And in fact, it holds for this much harder problem of covering IPs in random order, which I talked about earlier, which gets log m times n. Okay, so it avoids the double log loss. And actually, it's an improvement even over, do I have a laser pointer? Yeah, it's an improvement over this box in that we improve the support size term to an n. Okay, so it's just the number of elements you actually see in the sequence as opposed to the candidate elements I could have drawn from. And this is a new algorithm. It's not just a new analysis of an old algorithm. It's actually a new algorithm. And in some sense, what we're showing is that so this like upper left-hand corner is you're drawing from a known distribution n times, and the random order is more or less equivalent to drawing n times from an unknown distribution. Okay, and what we show is that it's possible to learn this distribution and to simultaneously solve the set cover problem without too big of a hit. Okay, so that's one result. And the sort of new thing is this part. We actually show you can get a log mn in the profit setting as well. Okay. Good, and everything holds for covering IPs for sort of a harder problem, but I'm going to talk about set cover in this talk. Any questions thus far? Please stop me, yeah. Good, so log n so I'm only talking about polytime algorithms. Log n, so log n is an information theoretic lower bound in all these models. There's a log m over log m lower bound, even if m is much bigger than n. So up to a log basically, yes. Yeah. Any other questions? And actually both of those are information theoretic. I glossed over this, the lower bound here of the double log does sort of, it's only for like polytime bounded algorithms. Okay, some bonus properties of this algorithm here. It works in the profit setting. It actually works in the single sample profit setting. So you don't actually even need to know the distributions. All you need is a single sample from each of those distributions, di. What's more, the algorithm is so-called universal or oblivious or non-adaptive. Okay, and I'll define what this means kind of later. But it's a nice property, and the selling point of this algorithm of Anupam et al. Was that it was universal, but this one required like full knowledge of the distributions. And kind of a bonus, corollary of this work is that we're getting sample complexity bounds for building kind of a universal algorithm, and I'll define what that means later. But yeah, okay, yes. Say that one more time. This one? I don't think so, actually. So the one you're thinking of is for deterministic algorithms, maybe. But for randomized algorithms, actually, I think the only one known is yeah, right. I'm glossing over, there's a slight difference between the deterministic model and the randomized model that's confusing to explain in the talk, but yeah. Okay. So we like talk outlines. This is the outline for the remainder of the talk. I'm going to spend most of the time on the secretary version, the random order version, and I'd be happy if we make it through the first part, even though it's older work, but it's the bulk of the talk. The single sample profit version is actually a reduction to the secretary model. Yeah, but hopefully we'll get through kind of a good amount. Okay. So what remains, I'll tell you about the secretary problem, the secretary version of set cover first. The algorithm that we give is called learn or cover. And I'll first show you an exponential time warm-up, which I hope everyone will be able to digest. Then I'll show you how to make this algorithm run in polytime, and then we'll do the profits and then conclusion and extensions. All right, let's jump in. So we had this question of where these two logs come from, and hopefully this will be clear soon. So how do we solve set cover? Before we jump into how we give this random order algorithm, let's talk about how you would solve set cover offline, just to make sure we're on the same page. Classic algorithm that we teach in approximation algorithms class. It's the following. I mean, there's many ways to solve set cover, but here's a convenient one for our purposes. We're going to solve an LP and then round the LP. Okay. So here's the LP for set cover. There's a variable for every set, XS. There's a constraint for every element saying fractionally you need to pick at least one set to cover that element, and everything must be non-negative. Okay, we know how to solve LPs. This is a relaxation, so the cost of the LP is less than the cost of opt. Great. Now, that's not a legit solution, it's a fractional solution, so we'll just buy every set with probability XS. If you do this, the expected cost is exactly the value of the LP. You're not going to be exactly feasible, but every element is going to be satisfied. Every constraint is going to be satisfied with constant probability. So if I boost this probability by log n, I can union bound over the constraints and basically satisfy all the constraints with high probability, and I'm done. Okay, so this gives an algorithm with expected cost log n times opt. Okay, log n came from the rounding. So far, so good. How do Alon et al. Do this online? They basically do the same two stages, but they solve the LP online. Okay, and what do I mean by that? Here's the same set cover LP. They give an algorithm, and this is kind of the heart of their work, a very cool algorithm that does two things. One is it guarantees that the x that you get at the end is log m, no more than log m times the optimum of this LP. And second, it has this magical property that x is only ever increasing monotonically. Okay, so if I drop the second condition, you could just solve the LP at every step and this wouldn't be interesting, but you're solving the LP with this monotonicity property. And now this is very powerful because if x is only increasing monotonicity, so, monotonically, excuse me, then suppose this is x at time t. X at time t plus 1 looks like this, right? It's only grown over time. What I can do is I can do the rounding. I can sample every set S with probability proportional only to the delta, okay, as opposed to the whole thing. And if I tune the proportionality constant cleverly, basically I can analyze this as if I'm rounding one single time at the end of the algorithm. Okay. So if this went over your head, it doesn't really matter for the purposes of this talk. The point is basically you can do the same two-step framework where I solve an LP and then round the LP, and I lose 2 logs this time. Okay, so the double log loss comes from the fact that you're solving an LP, but lossily, and then you're rounding again. So hopefully that answers your question. Okay, great. So we'd love to do this in the random order setting. Unfortunately, you can't. So neither of these stages can be improved. It's fairly easy to show that independent random rounding loses this log n. Okay, pretty much, yeah. No way to avoid this if you're going to do a union bound. What we show is that even if you're maintaining a fractional solution in random order, you have to lose the log m. Okay, so in other words, neither of these two stages can be improved in random order. And it's not just that the analysis is broken. Actually, we can also show that the actual Alon et al. Algorithm really does lose this double log on certain instances. Okay, so a new algorithm is needed. And one way to think of our result is that we are sort of maintaining a solution to the LP, but it's a core solution in that it's neither really feasible nor monotone, and yet can be rounded over time to give the guarantees that I'm claiming. This might seem somewhat mysterious, and I hope that it will be clear in a few slides. Any questions thus far? Great. Let's jump into our algorithm. Okay, so here's the exponential time warm-up. For this talk, we're always in the unit cost setting, so every set costs 1, just to be clear. Okay, here's the algorithm. We're gonna imagine we have two things in our head. Universe U, okay, and something I'm calling the portfolio. Whoa. Okay, script P. So the universe is like the elements that I have yet to cover, the uncovered elements, and the portfolio is initially, script S, which is all the sets, choose K. So it's all K tuples of sets, and K is a guess for opt. Okay, so using standard online algorithms tricks, I'm assuming I know the value of opt K. I know it at the beginning, and I'm thinking of P as everything that could be opt. Initially, I have no information. Every subcollection of size K could be the optimal solution. So that's my portfolio. Here's the algorithm. At time t, an element v arrives. If it's covered, no need to do anything, right? It's already covered, we're done. If it's not covered, we'll do two things. The blue step 1, is we'll choose a t uniformly at random from P. Okay, let's recall, P is the portfolio of all things that could be the optimal solution. Okay, so it's a K tuple of sets. Sorry, P is a collection of K tuples. And so if I sample T uniformly at random, that's a single K tuple. So I'll sample a T uniformly at random from P, and then from T, I'll draw a uniformly random R. So the type of R is a set. Okay? Great, that's step 1. Step 2 is I'll prune from my portfolio anything that I know is not the optimal solution. Yes? T is a K tuple. Wonderful. Single set, yes. Okay, does anyone see an issue with this algorithm? Yeah. Wonderful. Why is V and R? It's not. Great. So what we'll do is we'll buy another set to cover R, to cover V, excuse me. So great point. Yes. Oh, I'm sorry. So, okay, I should have changed this. I had this issue in the last talk. So from my portfolio, I'm thinking of P as everything that could be the optimal solution. The optimal solution is feasible. So if something doesn't cover the incoming element, it's definitely not the optimal solution. So I'll throw it out. So this is a different T, actually, sorry. This is like every T prime from my portfolio that does not cover the incoming element I know is not the optimal solution. So I'll get rid of it. Yeah. Wonderful question, yes. It seems like you should do 2 before 1. Yossi asked this question last week. It's easier to analyze. Yeah. Yeah, so hopefully you ask this question in a little bit. Hopefully it'll be clear. Yeah, it kind of decouples these 2 steps. Okay, we're clear on the algorithm? By the way, I have no sense of time, so tell me if I'm like, yeah. Okay. Analysis fits on this page. Okay, so case 1, at least half of the T in my portfolio cover at least half of the elements. What does this mean intuitively? Most of my portfolio is decent. Okay, at least half of the candidate solutions that I'm thinking of in my head cover most of the uncovered elements. Okay, in this case, I claim that the random R that I draw covers like 1/4K of the remaining U in expectation. Okay, why is this? Well, if half of T cover at least half of U, then the T that I draw should cover like 1/4 of U in expectation. And I'm drawing a random R from the K things in T, so that's like 1/K of that. So 1/4K. Good? Meaning U is going to shrink by 1 minus 1/4K in expectation. In my head, I'm imagining I'm throwing out all the elements that I've covered. Good? Great. Case 2. Okay, the negation of this, half of the T cover less than half of U. So most of the things in my portfolio are not good. Then because I'm drawing an element uniformly at random, right? So like if I hit this else clause, okay, that's basically drawing like, it's like sampling conditionally on the element being in the uncovered part of the space. Then I claim that I'm going to prune like a lot of my portfolio in expectation, okay? So most of my portfolio cover is like missing most of these elements. So if I draw a random element, it's gonna make me throw out a lot of the portfolio. In particular, half of the T and P are pruned with probability 1/2. You see this? Did you stare at this for a sec? So this means that P is going to shrink by 3/4 multiplicatively in expectation. Okay, I forgot to say this, I'm sorry. So in every round where an element shows up and it's covered, we pay 0. In every round when an element shows up and it's uncovered, we pay 2. I guess this buy should be in the else clause. Sorry. We pay 2 y, one to buy r, and then 1 to buy this backup set to cover the incoming element. So it suffices to count the number of times we land in this else clause. Okay, great. So the picture you should have in your head is that every time we pay 2, every time we land in this else clause, we're either in case 1 or case 2. We don't know which case we're in, but in case 1, we take a bite out of u, and in case 2, we take a bite out of p. And you're kind of marching through, and every time you take a bite out of one or the other. Okay. So let's do the analysis. So u is initially, the size of u is initially n. This is like the elements I need to cover. So how many times can n shrink by 1 minus 1 over 4k? K log n. Remember, k was my guess for opt. P is initially m choose k, which is something like m to the k. Right? It's all k tuples of sets, and there's m sets. How many times can m to the k shrink by 3/4 before I'm empty? K log m. Meaning that after I've done either k log n, these blue steps, which I'm calling cover steps, or k log m learn steps, the red steps, then I'm definitely done. So if I do k log m plus k log n, then I'm definitely done. That's it. Any questions? Okay, so let me do this proof, let's sort of write it in a slightly different language as an analogy to what's coming next. So I can basically argue the exact same thing with a potential function. Potential function looks like this: 1 over k times log of the size of p plus log of the size of u. I've color-coded everything suggestively. Did I get it right? Yeah, that should be red. Okay. And basically, you can do this proof like this. You can say, well, this potential function, it starts at log mn, right? Because p is like m to the k, so this should be like k log m divided by k, so that's log m. U is n, so this is log n, so this is log mn. It never goes below 0. And basically what I just argued to you in the last slide is that in expectation, this potential function decreases by something like 1 over k. You can do this math and you can work this out, but it's the exact same proof. Okay, so that was the exponential time version, and it was exponential time because we're enumerating all possible subsets of size k, subcollections of size k. Okay, so the next question is, how do you make this poly time, and can you reuse the intuition that you make progress either learning or covering? And I say learning because like every time you do one of these learn steps where you're trimming the portfolio, you're narrowing down, what could be the optimal solution. And cover is obvious why cover is called cover. Okay, great. So let's do the polytime version. Again, we're unit cost. So why did we need to enumerate, sets, like subcollections of sets? We really use this to like generate a distribution over sets. That's really what we're doing. So the natural thing to try to do is to just directly maintain a distribution over sets, and then to update this as we learn about the instance. So here's the algorithm. Initialize the distribution to be uniform. You don't know anything. Uniform over all the sets. It's going to look very similar. At time t, an element v arrives. If v is covered, do nothing. Otherwise, same two-step process. Just buy a random set directly from this distribution. That's step 1. Step 2 is update this distribution. Remember last time we did this pruning step to kind of make progress? Here we're going to give it a little nudge. So we know that the optimal solution needs to cover this incoming element. So let's give a little multiplicative boost to all the sets covering this element. Multiply them by e. E is the constant t. It doesn't matter. You can put any constant there, but it's just neater. And then we'll renormalize so that it's still a distribution. And once again, we'll do this like this backup step. And I guess I put it in the else clause on this slide. We're good here? Make sense? By the way, sorry, Jelani, did I answer your question about why these things should be, why it's easier to analyze them? I don't think I answered. So basically, like if you do 2 before 1, then the distribution now depends on the element that you sample. Whereas if you do this first, they're sort of very independent. Okay, so yeah. Okay. Okay, so the idea, I guess I foreshadowed it, is to measure convergence with a potential function this time. And the potential function is like this. It's basically the KL divergence. Yeah. E is the constant, like 2 point whatever. Yeah. Yeah. Yeah, you should, except that it's different. So you can the Alon et al. Algorithm that I referred to is like a multiplicative weights type algorithm. I didn't actually tell you how they maintain a fractional solution, but they are doing multiplicative weights exactly. Except that notice here, I'm not saying like do this until the solution is feasible. I'm just saying give it one little push. Okay, so yes, it is like a multiplicative weights algorithm, but it's different from that one in that they project all the way to feasibility. They don't have this normalization step, and this is sort of what's new here. So it is, but it's different. Yeah, good. And there's a lot of proofs of like you know, like experts regret bounds that go through the KL divergence as well. So yeah, there's a connection. Okay, so here's the potential function. It's the KL divergence between x star and xt. X star is the uniform distribution on opt, and think of this as the optimal distribution I should be sampling from. And xt is my current solution at time t. Plus log of the number of uncovered elements. So this blue part's actually exactly the same from the last section. This part's now changed. Okay, and this is the KL divergence if you haven't seen it before, but we're not going to sort of do the algebra, so it's not going to matter too much. But basically, we have the same proof outline, which we can make work in this setting. So this initial the initial potential is bounded by log mn, excuse me, doesn't go below 0, and then every time an element is uncovered, every time you hit this else clause and you pay 2, this potential goes down by 1 over k. Okay, so it's think of it as this bank that's loaded up with log mn. Every time I pay, the bank decreases by 1 over k. How many times can this happen? K times log mn. Say pay like 2 times k times log mn. Good. Okay, maybe this is a better answer to Jelani's question again. So the proof goes by bounding the decrease in the blue part over just the randomness in the R that I buy. And then the decrease in the KL divergence, I bound over the randomness of just the incoming element V. And if I flip the order of these two things, then the decrease in the blue part would depend on both, which would be nastier to analyze. But I agree, it's a strange, it's a little strange that you do, yeah. You'd think that, yeah. Yes. I don't know. Yeah. Yeah. Maybe. Okay. And crucially, we're using the random order here, right? So this problem has a double log lower bound in adversarial order. You have to be using the random order. Yeah. Good. Okay, so I'm not going to really do this proof, but roughly here's how it goes. So we can bound the change in the KL divergence by this expression, and you can bound the change in the blue part by this expression. The important part is that the KL divergence has a positive term and a negative term, and the positive term looks a lot like the negative term in the blue part, just scaled. And so if you scale set these C1 and C2 appropriately, you can basically make the decrease negative 1 over k, which is what you wanted. And so these things like fit into each other nicely, and we get our proof. Okay, so this is how we argue that the total cost is k times log mn. Any questions? Yeah. No, it doesn't. Yeah. So we can break it, which is interesting. Yeah. But it's easy to run like a combiner algorithm. So you can always, yeah. What is, I don't even know. Yeah, but it's, I forget. It's, yeah, it's a while ago. But it can be pretty bad. Yes. Good. Yeah, so we showed a sort of weak lower bound, and then someone at a talk I gave told me that there's a trivial demonstration of this, and so we yanked it. But okay, so here's what we can show. So there's like n factorial permutations. So the entropy of that is like n log n. And you can ask like how much entropy like do you need to get this bound? And basically, okay, here's the statement we can show is that there are distributions over permutations with entropy 1 minus epsilon times n log n, such that you get like a double log lower bound with like a 1 over epsilon sort of hit. Okay, but actually, it's not that interesting of a theorem. But at least entropy is not a good way to parameterize the randomness. You can ask other questions like, yeah, but I don't know. I don't know the answer. Yeah. Yes. Sorry, say it again. Oh, like you talking about like bit complexity sort of issues? Sorry. So the problem, remember there was this like bipartite graph? There's some like small number of sets, m sets. I'm allowed polytime in m, the number of sets. So I don't have the whole power set. Otherwise it'd be easy. I'd just pick the biggest set I've seen so far or something. Yeah. Yeah. So far so good? Okay. How much time do I have left? Okay. Yeah, so we'll get as far as we get, and that's fine. Okay. Oh, okay. So this proof, I'm sorry for flashing some math at you. Some people did this today as well. The point is just to show you that it fits on the slide, basically. It's really not so bad, and it uses like inequalities that you learn, pretty early. There's like nothing super fancy. Okay. You can, find me later. I can show you this proof if you're really interested. Okay, great. So some philosophy, like what did we do here? I alluded to this, Sherry, per your question. So can you see this this text in pink here? So the Alonadal algorithm, you can think of it as follows. You're in some like polytope, polyhedron, whatever, and you get a new constraint, an element that's uncovered. Okay, you're not satisfying it. What they do is a projection in KL divergence onto that constraint. Okay, they find the point in the new feasible region that's closest in KL divergence to my old solution, and they project onto the space. Okay, that's one way to interpret their algorithm. What we're doing is not quite that. It's similar. So we do a kind of nudge towards the same projection. And then we're renormalizing back onto the constraint that like our cost be the same as the cost of opt. That's one way to interpret our algorithm. Okay, so that's highlighting the difference. Here's another suggestive perspective that I hope one of you will interpret for me. Let's write this function f. Okay, f of our solution x is the sum over the elements of the max of 0 and 1 minus the sum over S containing V of xs. So stare at this for a sec. This is the fractional uncoverage of my solution. How much I have yet to cover. We want to minimize this function, right? We kind of want to find a feasible solution x that has this function at 0. Suppose we're sort of, trying to minimize f in the smallest number of steps. Okay, bear with me for a sec. Good. So the gradient of this function f, okay, the gradient is a vector, and the coordinates of this vector indexed by sets. But the gradient of this vector is the number of uncovered elements in S, which is proportional to the expected value of the indicator of whether or not the incoming element is uncovered. So basically my point here is that the random order is revealing the stochastic gradient of this function. And you can kind of think of what we're doing as running stochastic gradient descent on this function. Of course, it's like mirror descent with whatever entropy mirror map, but this is yeah, like another perspective on this algorithm. Every time we take a step here, we're like paying 1. We're buying like 2 sets per round, and so we're kind of asking like about the convergence rate of SG, or it's a yeah, but it's a little yeah. This analogy breaks down in the weighted setting, so I'm not sure I fully understand this perspective, but it's food for thought. Okay, any questions? Yeah. Which one? Oh, I'm hiding some things from you. So remember I said you're making it a distribution? You can think of it like as projecting onto the cost equals cost of opt is like a scale distribution, where yeah. But it's an analogous. For the costed setting, you kind of need to think more generally as like projecting onto this constraint. Yeah. But essentially, it's that step. It's when you renormalize to make yourself a distribution, you're morally doing this. Remember I said X star was, sorry, okay, it's too much to step through. X star I said was the distribution over things in opt. Yeah. So the L1 mass is 1. Okay. Okay, so that's all I have to say about the secretary version, and let me spend a little bit of time on the profit setting. Okay, so we're going to talk about the special case. So remember I said the profit setting is you sample from D1 through Dn. We're going to assume that D1 through Dn are all the same. And morally, this is the same as the following problem, which I'm calling the online set cover with a sample. Again, we're in the single sample setting, recall. Okay, we don't even know the distributions D1 through Dn, which is the same distribution, but we have a single sample from each, which is kind of the same as if I've like sampled, I have half the input up front, which is kind of the same as if every element is known up front with probability 1/2. We're doing a lot of leaps of faith, but just, morally accept that this is the same problem. Okay? Is this problem clear? Playing online set cover, but you see half your input up front. So let me do this in a picture. The remaining half is revealed in adversarial order. So this is the online set cover game. We have our bipartite graph. We know the left-hand side. Half of the elements are known to me in advance. Okay, uniformly at random. And then we maybe cover them, and then the remaining half is revealed in adversarial order. So this element shows up, it's already covered. This one shows up, it's already covered. This one shows up, it's not covered. I'll buy a set to cover it. Is the model clear? Okay. So here's the theorem. There's a polytime algorithm for online set cover with a sample with comparative ratio order log mn. Here's the idea: reduction to learner cover. It's not quite a reduction to the random order setting. It's we need specific properties of the algorithm. But it's still a reduction. Okay, so here's the idea. The algorithm is just going to be run learn or cover on the samples, like shuffle those in random order, pretend that they're coming in random order. And then for the remaining elements, some of them might still be uncovered, right? The ones that are revealed in adversarial order, we'll just buy an arbitrary set to cover any of those if they remain uncovered. Okay, so here's the idea for the analysis. We'll pretend, okay, the pink were the sampled elements and the blue were the adversarial ones. Let's imagine this like fake process on our heads, where every element shows up and then on arrival tells me if it's pink or if it's blue. Okay? So an element shows up, so here's this like fake model. Okay? And then on arrival it decides, okay, I'm blue. And then another one arrives and it's, okay, whatever, so on and so forth. So like on arrival, we're deferring the randomness of like which half it's in, the sampled or the adversarial, to like the arrival time of this thing. And then we're going to run this like fake algorithm on this fake process, okay, this imaginary process. If it's pink, feed it to learn or cover. And if it's blue, buy an arbitrary set to cover it. The point is that, okay, even though this is a fake process, the cost of our algorithm is no more than we pay on this fake process. So it's going to suffice to bound how much we pay on this in this fake world. Is this clear? Do you see why this is the case? Basically, like our algorithm is going to pay the same on the pink elements, and the blue ones we actually only see like after we've seen all of the pink elements. And in this is actually like a harder setting, because the blue ones like might show up before I've seen all the pink ones. So I might sometimes pay extra for them. But okay, that's only more. So I'm going to bound the cost of this thing. recall the learner cover proof template. I had an initial potential function, and I said it decreases by 1 over k whenever an element is uncovered. So now the potential is only going to decrease during pink steps, right? Because I'm only getting a random element during the pink steps. And I needed this random, right? I had to say that like my elements are coming in uniformly random order, which is the same as being sampled uniformly from the uncovered part of the space. So I only get a decrease with probability 1/2, but that's still omega of 1 over k. And so this proof template basically goes through. Does that make sense? Any questions? I know it's late, I'm sorry. So it's a harder model even. It's like half of it is in random order and then half is adversarial. Okay, so the actual model, this is like a fake setting. The fake setting. The point is just that like I'm saying like the blue ones I'll pay for later. It doesn't even matter. Like I'll just commit to like paying for them later. Does that make sense? Let's stare at this for a sec, yeah, because it's confusing. Good, yeah. So okay, so if a blue one shows up and it's uncovered, I'll just pay 1 on the spot. That's the model. So basically I'm seeing elements with probability 1/2 they're pink, and then they're like a truly kind of random sample, and then if they're blue, like later I'll just pay 1. Okay, that's it basically. That's the algorithm. And more or less a similar, yeah, we're happy. A similar thing works in the profit setting. You need to be a little more clever, but it's basically this idea. Okay, bonus that I promised for this algorithm is it's universal, and I'll finally say what I mean by universal. Oh God, I forgot to do the order, whatever. What do I mean by universal is this algorithm is actually building a map F that maps elements to sets during the sample phase. And then what is it doing? When an element U arrives, this algorithm commits to buying F of U. So meaning, before it's even seen any of the elements that come during the like actual, the actual adversarial part of this process, it's already committed to what it's going to do. It's like highly, highly non-adaptive. That's clear. So that's what I mean by universal algorithm. It builds like a map of what it's going to do before it's seen any of the input. And the point is that actually we could build this universal map with only order n samples. So this is what I was saying about we're getting the first sample complexity bounds for building such a universal map. Any questions? This is the end of the talk. Yeah. Okay, great. So some conclusions. This is the theorem that I claim to you. So the two theorems. So log mn competitive algorithms for random order covering IPs and the profit version of covering IPs. That's cut off. Sorry for conversion issues. And as I said, as a bonus, we get like this in the single sample world, and it's universal. We have extensions to this result, so we can show the same thing for non-metric facility location, and we can show a lower bound of a double log for a problem that's like much harder in the covering hierarchy. Okay, so you can kind of define harder and harder covering problems. Something called submodular cover and like an online variant of submodular cover in random order doesn't get easier. So you do need to lose a double log. I haven't told you what this parameter is, but it doesn't matter. And the open problem that I talked about, the open problem session, was for box constrained covering IPs, which is in between covering like pure covering IPs and submodular cover. And I want to nail down like where the threshold is between single log and double log. So hopefully that's useful context. Open question: does learner cover lend itself to other problems? Harder covering problems, covering IPs with box constraints. And is there like a unified theory? I kind of just threw this out here. A unified theory of random order algorithms. Like is there, this algorithm is very simple. And okay, we realized the random order version last year, and then we kind of have been finding more applications. Is this something like kind of fundamental, and are there more, are there interpretations of old random order algorithms in this learner cover lens? With that, thank you, and I'll open the floor to questions. Yeah. Thanks for sticking around.